my name is Joseph Wong. I'm going to be a second-year physics major in the College of Creative Studies. I've been working with my mentor, Dr. Elena Henry, and my research advisor, Professor Crystal Martin, on identifying faint galaxies. So our ultimate goal with this project is to study this really interesting feature of galaxies called the mass-metallicity relation. And what previous research has found is that if you compare a galaxy's stellar mass, that's shown here on the x-axis, with its metallicity, that is the proportion of heavier elements, anything heavier than helium in astrophysics terms, that there's a correlation between them. And not only that, but where exactly a galaxy lies on this graph is a very interesting indicator of its evolutionary properties. Now, this has not been studied in a huge amount of detail yet. This figure is from the first paper that ever discovered it. And what more recent research has found, is that different samples give different slopes here. And as you may also notice, this only goes down to about 10 to the 9th solar masses. So we're interested in studying it at lower mass objects too. So the way we identify the galaxies that we're looking at is, before I got to my research group, what they did is they did a spectroscopic survey of a small portion of the sky. And the way they did it is they pointed this slit mask, and based on the way light diffracts through the slits, you can find emission lines. Now, there are a few things about this. First of all, it's only looking at a very small portion of the spectrum, so you can't tell the entire spectrum of emitted light from objects you see here. It's just a few emission lines. And there were two types of objects identified here. One was the very distant objects that Jacob talked about this morning. Those are about 14 billion light years away. And the other type are the closer objects that I was looking at. Those are closer to about 6 billion light years away. And they're identified by 3 very close emission lines in this spectroscopic survey. So just a little bit of background. When we look out at distant objects in the universe, what we see is that they're moving away from us based on the expansion of the universe. And not only that, but farther objects are moving away faster. And what we know from physics is that when an object is moving away, the light that we see is going to be redshifted. And not only that, but how fast it's moving away will influence how much is redshifted. So in order to determine where objects are, or at least we're really more interested in their redshift, but it's related to distance, we look at different spectral features, and based on how much they're shifted in the spectrum, we can tell the redshift. So in this spectroscopic survey, there were about 34 objects that were in that foreground sample I was talking about. And they're all pretty faint and pretty light, but in particular there were 6 that were very faint. So faint, in fact, that they were first mistaken for those very far objects that Jacob was talking about this morning. But it later turned out that they were, in fact, these foreground objects with the 3 emission lines. And the problem with those is that we're really not sure. We need some data from existing telescopes in order to tell certain properties about them, like the mass. But we're not sure if they're even bright enough to be identified in existing telescope data. So what I did is I took all this telescope data. This is coming from a bunch of ground-based telescopes. This was done all before in these big surveys. And this is a 5 arcsecond window. 5 arcsecond squared, that's about 1/1440th the width of the moon, so pretty small. But these objects are decently far away. And each of these is the same section of sky, just viewed through a different filter, which basically just restricts the amount of the light that's coming through to a very narrow portion of the spectrum. Not too narrow, but pretty narrow. And what's done is all the light coming from these objects is added up in each of these. And then from those, what you get are these little points here in green. Each of them represents a different filter image with all the light added up. And then what we can do with those is, in order to verify that these objects that we're seeing in these images are in fact the objects we identified with the spectroscopy, is we can fit templates to them of what galaxies should look like. And you'll notice on the left here, this is a good fit. And that is that the data points line up very closely with the template that we fitted to them. But on the right, it's a little bit fuzzier. It's because the points are all over the place, and also the error bars are a lot larger. And it turns out most of the objects that I was looking at, those 6, fall into the latter category. They're pretty loose fits. So we can't say for sure from this that they're the objects we're looking at, but we have a few other techniques to look at too. So when the code fitted these templates, what it does is it shifts them back and forth and measures the error between the actual measured data from the telescope and the template. And that produces this statistic called chi-squared, which is shown on the y-axis. And so we can produce these plots of redshift versus chi-squared. And since we want to minimize error, it looks good when we have a dip in chi-squared right where the spectroscopy identified the redshift. What you may notice here is that there are a few dips in this plot, so we're not entirely sure, but it's very promising that we actually see these very narrow gaps right where the spectroscopic redshift is. And it turned out to be, we saw these dips for most of the objects, so it's a good indicator that these are the objects we're in fact looking for. The last thing we can do is just make a statistical argument. We have a little bit of uncertainty about the exact position of the object. In particular, we know pretty well where an object is along those slits, but going between slits, we've got a decent amount of error. You can see that this ellipse of position uncertainty is a lot larger in the vertical direction. So what we can do is, in this telescope data, they've identified all of the relatively bright objects, and there are 250,000 of those in the field. And the field itself is about 51 million arcseconds squared, but this little ellipse is only 0.47 square arcseconds. So the typical number of objects you're going to find in that ellipse is 0.002. So the fact that we find these objects here to begin with is a very good argument that these are the objects we're looking for. And not only that, but the objects we found are brighter than about half the catalog. So that means that it's extremely unlikely that we would have found other objects in this field, and just the objects that we found spectroscopically were just too faint to identify. And especially if you consider that we have 6 different objects, the probability of getting it wrong in more than one is extremely low. So I'd like to thank my mentor, Dr. Elena Henry, my PI, Professor Crystal Martin, Tyler, EUREKA, and Ophelia Aguirre for organizing the EUREKA program, and our sponsors, EUREKA, NASA, the David and Lucille Packard Foundation, and the National Science Foundation.